You ever stare at a math problem, something out of your calculus textbook and just think, nope, no way. It looks like this total mess of symbols, like it's designed to be unsolvable. Well, guess what? Even the most intimidating problems have a clear path to an answer. You just have to know the strategy. And today, we're going to walk through that strategy and solve one of these impossible integrals together.
Okay, so check this thing out. It's a bit of a monster, right? You've got a polynomial on top of another polynomial, like where do you even start? U sub? Nah, doesn't look like it. Integration by parts? Oof, that's just going to make it worse. This is exactly the kind of problem that feels impossible. But don't worry, we're going to take it apart piece by piece.
So the very first step, and honestly the most important one, isn't just to start crunching numbers. It's to stop and figure out what we're actually looking at. The whole secret to solving this thing is realizing that not all fractions with polynomials are created equal.
It all comes down to the degree of the polynomials. And that's just a fancy way of saying the highest exponent on the variable, right? If the top degree is smaller than the bottom, we call that proper. But if the top degree is bigger or even the same, it's improper. So for our problem, we've got a degree of 3 on top and 2 on the bottom. Yep, definitely dealing with an improper fraction here.
This might sound kind of abstract, but I promise you already know how this works. Just think back to grade school. A fraction like 3/4 is proper. But 5/4, where the top is bigger than the bottom, we called that an improper fraction. It's the exact same idea, we're just using polynomials instead of numbers.
And what do we do with improper fractions like 5/4? We simplified them. We used division to turn it into a mixed number, right? 1 and 1/4. Well, that's our game plan. Improper just means there's a little bit of work we need to do up front to simplify it before we can get to the calculus.
And the tool for this job is one you probably haven't thought about in a while. Polynomial long division. Yep, it's the technique we use to divide one polynomial by another, and it's exactly how we're going to tame this wild fraction and make it something we can actually work with.
All right, so how does this work? We're going to set it up just like the long division you did back in the day. Now, here's a pro tip. Add a 0x squared as a placeholder. It just helps keep everything lined up. Okay, now we just look at the first terms. X cubed divided by x squared. What's that? It's just x. Perfect. So we put that x up top, multiply it by the divisor x squared plus 1, and then we subtract. What we get left over is 4x plus 10. And we can actually stop right there, because the degree of our remainder is now smaller than the degree of our divisor. It's as simple as it's going to get.
So check this out. This is the big transformation. Our original messy fraction is now equal to x, that's what we got from the division, plus the remainder, 4x plus 10, all sitting over our original divisor. We've turned one big, ugly problem into two much nicer pieces.
And this shows you exactly why that first step was so important. Our scary integral is now split into two parts we can actually handle. The first part, the integral of x, that's about as easy as it gets. And the second part is now a proper rational function, which means we have a whole new set of tools we can use on it.
Okay, so let's focus on that second piece. For this, we're going to use a super powerful technique called partial fraction decomposition. It's basically the art of taking one complicated fraction and shattering it into a bunch of simpler little fractions that are way easier to integrate.
Now, how we break it down depends completely on what the denominator looks like after you factor it. There's a clear recipe for every single case. If you have different linear factors, you get simple terms like a over this and b over that. If you've got repeated factors or quadratic ones, the rules are a little different, but it's always a predictable pattern. This isn't guesswork, it's a system.
Now, usually finding those constants, the a's and b's and all that, can involve some pretty boring algebra. But for the simplest case, when you have distinct linear factors, there is an incredible shortcut. It's called the Heaviside cover-up method, and it seriously feels like a magic trick.
And this isn't just some little trick your professor made up. It comes from Oliver Heaviside, a brilliant self-taught physicist and engineer who needed to invent powerful math to solve real problems. So this method, it was born from a need to get things done fast and efficiently.
Let me show you how this works. So you have this fraction here. To find the a that goes over the s minus 1, you literally just cover up the s minus 1 factor on the left with your thumb. Now plug s equals 1 into whatever's left. Boom, you get a. Then for b, you do the same thing. Cover up the s plus 2 factor and plug s equals -2 into the rest. It's just so fast. You get the answer without having to do all that heavy algebra.
So it looks like magic, but it's not. All the cover-up method is really doing is taking the normal algebraic process and squishing it down into one quick step.
It's just a shortcut for multiplying out the whole equation and then plugging in the special value of s that makes one of the terms disappear. It's absolutely brilliant.
Okay, we figured out what kind of problem we had. We used long division to make it simpler. We learned how to break down the leftover piece. Now it's time to put it all together and finally solve the integral that started this whole thing.
So here it is, our roadmap, our 4-step plan to get from total chaos to a clean solution. First, check the degrees. If it's improper, use long division. Then, decompose what's left over. And finally, the easy part. Integrate each of those simple little pieces one by one.
Remember this thing? The problem that looked so awful at the very beginning? Well, it's time for the big payoff.
After we did our long division, we had the integral of x plus the integral of our remainder. And that remainder, 4x plus 10 over x squared plus 1, we can split that into 2 more fractions, 4x over x squared plus 1 and 10 over x squared plus 1. And just like that, what started as one big mess is now a sum of 3 basic integrals that we totally know how to solve.
And here it is, the big finale. The integral of x, that's just a simple power rule, x squared over 2. The second part, that 4x term, that's a classic u substitution, which gives you a natural log. And that third piece, the 10 over x squared plus 1, that is the textbook definition of an inverse tangent. So you just add them all up, don't forget your constant of integration, your trusty plus c, and we're done. We started with something that looked impossible, and just by following a clear strategy, we ended up with this really clean, elegant solution.
And that, right there, is the real point of all this. The next time you see a problem that just looks overwhelming, whether it's in math or anywhere else, just remember this process. That impossible problem, it probably isn't impossible at all. It's just waiting for you to find the right strategy to break it down into something you can actually solve.